Section 4.3, solving friction problems. So the strategies used here will be very similar to what we did in Chapter 3, but we're going to introduce a little bit more of that force of friction calculation into this. So by the end of today, I'll be able to solve multi-step problems that include a friction force. They might even include some kinematics, so we'll keep that in mind. It is important to understand, though, that friction is a force that can be both beneficial and detrimental depending on what we're trying to accomplish. So friction is the force that allows us to walk across a room or drive down a road. It's the force that keeps our shoes tied and reshapes our planet in the form of erosion. Coincidentally, it also keeps your socks on. Okay, no friction, no socks. However, friction between parts in an automobile is what reduces the efficiency of the machine and creates excessive heat in the engine, and it's the same force that makes it really difficult to move heavy objects. So there are times where it's good and times where it's not so good. So back to the sleds. Okay, so two sleds are tied together with a rope. The coefficient of static friction between each sled and the snow is 0.22. Okay, now what you'll notice what's different between Chapter 3 and Chapter 4 is that in Chapter 3 they just told you the friction. Now in Chapter 3 you have to go and figure out the friction that's acting on each sled. That's probably the biggest difference. Okay, so a small child is sitting on sled 1, total mass of 27 kilograms, and a larger child sits on sled 2, 38 kilograms. An adult pulls on the sleds. So first question is, what is the greatest horizontal force that the adult can exert on sled 1 without moving either sled? Okay, so we're going to view this as a system problem. So I'm going to draw this here. This is my 38 kilograms plus 27 kilograms. I shouldn't have started writing that. That's going to be 65 kilograms as a system. So now if I find my FG, 65 times 9.8, I'm going to get 637 newtons. Okay, now again, the sleds are not jumping up into the air, so my normal force will also be 637 newtons because they're in equilibrium. Okay, so we have our Fn, we have our 0.22. Okay, so if we grab our coefficient of friction expression, and I have to admit I'm a little bit lazy sometimes on the S's and the K's, mostly because of comfort. Okay, so I have a coefficient. I know this 0.22. I know my normal. I should be able to calculate the force of friction, and that we could call it max if you want. That force of friction is what I'm going to have to overcome before anything moves here. So if I put a 0.22 and then my F max and my normal force is 637. So if I take my 637 and I times it by 0.22, better do that right, times 0.2, I get 140 newtons would be my, and I should use an S there I guess to match the textbook, but that is my force of friction max. So the adult would have to pull with 140 newtons or greater before this would start to move. So part B, calculate the magnitude of the tension in the rope between sleds 1 and 2 when the adult exerts this greatest horizontal force but does not get the sleds to move. Okay, so I'm just going to get rid of this part here. Let's move the 140. So we already know our Fs max is 140 newtons. So this is 140 newtons. And we'll just carve out a little bit of room here for ourselves. Okay, so calculate the magnitude of tension in the rope. So I want to draw a quick little free body diagram. I'm going to do it on sled 1. Okay, so I have Fa, which is the 140 newtons. Okay, I have, now here's where I got to be careful. There is a force of friction acting on that sled, but there's also a tension force from the rope going back to the sled. So when I start to size this up, I see there's a lot of things that I don't know. Some of them I could calculate. I know Fa. I could calculate force of friction. Okay, and I can find Ft, which is what it's asking me for. So there is a chance of doing this. I could have also tried to work with sled 2. You might have found a slightly different problem, but let's try this. So let's go F net. We know this is 140 newtons. I'm going to say positive is to the right. My force of friction, okay, I want you to watch how I'm going to write this. Actually, I'll put an extra line in. Force of friction, and then minus my tension force. So F net, that's mass times acceleration. So the mass of the first sled is 27. Do I know the acceleration? Of course I do, because they're not moving. That was the key piece. It does not move. Not moved. So my A here is 0. Okay, there's the 140. And now my force of friction is going to be, I'm going to rewrite it like this, minus Ft. Okay, and I also know that the normal force is going to be mass times gravity. Okay, so I can do a bunch of things at once here. So 0 equals 140 minus 0.22 times the mass of the child, which is 27, times gravity, minus Ft. Okay, so I'll give you a second if you want to try that. I'm going to give myself a little bit more room here to solve. So now 0.22 times 27 times 9.8. Let's say it's 58.2. So I have 0 equals 140 minus 58.2 minus Ft. If I solve for Ft, I get 140 minus 58.2, or 81.8 newtons is the tension in the rope. Okay, so pause and try these. I'm going to set up the answers to these in a separate video so this doesn't go on forever. So if you want to try it and you don't get the right answers, I'll have a separate video that talks about these. I do that a couple times today. So pause it, give them a shot. Okay, welcome back. So here are the solutions to the first one. So 290 newtons, 120 newtons to the right. And then number 2, 0.45. Okay, so again, those solutions are in a separate companion video. Okay, so now kinetic friction problems. This is just more of a clarity piece than anything really new. We sometimes think that the force of friction, all it does is it makes the F net smaller, and that's generally this one right here. So you have an applied force moving to the left, the force of friction is to the right, so you have this F net that gets really small. But there are times where both the FA, the applied force, and the friction force will be in the same direction, and you'll notice it makes the F net larger, which is a little bit different. So that's just something to think about. You don't have to memorize or anything like that. It just really reinforces the idea that the free body diagram is critical for problem solving. Okay, so here let's try one. Stopping a sliding box. A 250 kilogram box slides down a ramp and then across a level floor. The coefficient of kinetic friction along the floor is 0.2. A person sees the box moving at 1 meter per second left and pushes on it with a horizontal force of 140 newtons to the right. How far does the box travel before coming to rest? Okay, so you have some sort of situation like this. There's a box, slides down, and now it's sliding across the floor. Okay, so let's draw a quick free body diagram of our box here. It is 250 kilograms. So I'm going to do a couple quick calculations. So Fg on that is going to be 2,450 newtons. That means my normal force, again, will be the same because it's not on the ramp, it's on the level floor. The ramp would be more of a grade 12 problem. The coefficient of friction is 0.2. So if I look at horizontal forces, this thing is moving to the left. Okay, so that's our V, it's going to the left. So I have a force of friction that is opposing the motion, but I also have somebody pushing. So I have an applied force pushing to try and stop this object. Okay, so when we go to solve this problem, again, we're going to do our FNet statement. I'm going to define positive is to the left because that's the direction of motion. So FNet here would be negative force of friction minus FA. So take a second and think about that. So both of those forces are acting against the motion of the object. Okay, so FNet is mass times acceleration. Force of friction is going to be 0.2 times the normal force, which is 2,450, and we're also going to subtract the 140 newtons. Okay, that's a 4 of the applied force. Okay, and the mass here of this object is 250 kilograms. Okay, so we could even get rid of that m right now and save ourselves a line. So let's just get rid of that guy right there, and we'll put in 250. Okay, so now I have 250A equals, now let's do this real quick, 0.2 times 2,450. So that's a negative 490 minus another 140. So I get negative 630 newtons. And now the negative should be comfortable because it's an acceleration that's in the opposite direction of the motion. So it's trying to slow us down. We divide both sides by 250 and we get an acceleration of negative 2.5 meters per second squared. Okay, so now how far does the box travel before coming to rest? So now this becomes a kinematics problem. Yay, I know you're excited. Okay, so let's list what we know. We know we have a VI of 1 meter per second. We know we have an acceleration of negative 2.5 meters per second squared, and it comes to rest, which means VF is 0 meters per second, and we're trying to find D. Okay, so if we go VF squared equals VI squared plus 2AD. Okay, so VF is 0. This is a 1 squared plus 2, negative 2.5, and a D. Okay, so I'm going to end up with, I'll just do a quick rearranging. This becomes negative 1. This becomes negative 5. If we divide negative 1 by negative 5, let's give ourselves a little more space. We get 0.2 equals D. So 0.2 meters is the stopping distance. Okay. We'll try one more sled question if we've got time here. Two sleds tied together are pulled across an icy surface with an applied force of 150 newtons. Got that. The mass of sled 1 is 18 kilograms. I'm going to write that down right now because I find that helpful. Mass of sled 2 is 12 kilograms. So I've got a 30 kilogram system here. The coefficient of kinetic friction is 0.2. Calculate the acceleration of the sleds. Okay, so I'm looking for an acceleration. So in my mind, that's triggering at Newton's third law, F net, m equals a, or sorry, not third law, second law. Okay, so I'm already thinking about ma. That F equals ma is sort of on my mind already. Okay, so if we draw this as a system, I have a 30 kilogram object. It's got 150 newtons pulling this way. It has some sort of force of friction opposing that motion. So if I write an F net statement, I'm going to say positive is to the right. So I have 150 minus, now my force of friction is going to be mu times the normal force. So this is my force of friction. I'm just being a little bit quicker here just to try and minimize the number of lines. So let's slide down a little bit and give some more room. So now I have mass times acceleration, 150 minus, this was 0.2. The mass of this object is 30, and gravity is 9.8. Okay, so I have most of the important numbers written in there. Let's just do a quick solution. So 30 times A, I need to calculate 0.2 times 30 times 9.8. It's 58.8. We'll just leave it at that for now and see what happens. Okay. So if I have 150 minus 58.8, I got 91.2. Divide both sides by 30, and I should get approximately, let's just say that's 3 meters per second squared. So I have my acceleration. Okay, so acceleration here is a equals 3 meters per second squared. Determine the magnitude of the tension in the rope between the sleds. So I'm going to choose sled 2 because I feel like it. Okay, so there's some sort of tension force here. There's some sort of friction force here. So I write my F net statement, and that's going to be Ft minus force of friction. Okay, so this is going to be mass times acceleration. Ft is what I'm looking for, and this is going to be mu times the normal force. Okay, so the mass of sled 2 is 12. Ft is what I want. This is going to be mu times 12 times 9.8. I guess I should have erased this and given myself a little bit more room, but we can persevere. We'll get through it. My acceleration is 3. I could have added that in as well. So let's just cover that out and put a 3 in there. So now I have 36 equals Ft minus, and this was 0.2. So 0.2 times 12 times 9.8, 23.5. Okay, and if I solve for Ft, I'm going to have 36 minus 23.5, and I should get 12.5 newtons equals the tension force. Now hopefully you're starting to see, after doing a whole bunch of these, there is a process. The process works really well if you stick to it, and I'm going to encourage you, please, please, please try and follow the process because it will guide you through trickier, more difficult problems. Okay, so pause and try. These are ones you can try. And again, I'm going to put all these solutions in a separate video because we're already getting a little bit up there in time. Number 4, an electric motor question. You can see the solutions video for the answers to here. That leaves us with section 4.3, 5 questions to try, 1, 2, 5, 7, and 8. Thank you for listening. I know that was a bit long, but I appreciate your time.